Welcome to the class, my dear student. In the last class, we have already discussed the two colligative properties. In this lecture, we will be going to discuss the third colligative property, that is elevation in boiling point. This is our third colligative property, elevation in boiling point. Okay, so first tell me, what is boiling point? Anybody in the class know what is boiling point? Anybody? Yes, Sumit, tell me. Yes, Sumit, tell me, bete.
And boiling point is a point at which a substance start melting.
Okay, yes, it is correct. Boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. In terms of pressure, in which the boiling point is the temperature at which, yes, it is correct, the substance start boil at which the vapor pressure of liquid becomes equals to atmospheric pressure. Okay, this is your boiling point. For example, the boiling point of water at 100 degrees Celsius is 1 atmosphere or 1.013 bar. You know this? Okay, it is 100 degrees Celsius at 1 atmosphere. This is the boiling point of water. Now, it is found that the boiling point of the solution is always higher than that of the pure solvent. This is your increase in boiling point or elevation in boiling point, because the vapor pressure, because the boiling point of solution is always higher than that of pure solvent. Why? Because the vapor pressure is solution is always less than that of pure solvent, and more the vapor pressure, low is the boiling point, or vice versa. So the vapor pressure of solution is less. That's why the boiling point of solution is more than that of pure solvent. I hope it is clear to you all. I hope it is clear to you all. And this is your elevation in boiling point. Okay. Now I am going to discuss the elevation in boiling point with the help of graph. We are going to discuss it with help of graph. Suppose I am going to plot a graph between vapor pressure and temperature. Vapor pressure and temperature. I am plotting the graph for a particular solution or a solvent. For example, this graph is for a solvent and this graph is for a solution. This is for solution. This is for solvent. So, my dear, suppose this AB graph represents for solvent and CD is for solution. So, dear, vapor pressure of the solvent increases with the increase of temperature. Similarly, for solution also. As at any temperature, the vapor pressure of solution is less than that of the solvent, the curve of the solution lies below the solvent. Now, the temperature at which the vapor pressure of the liquid becomes equal to atmospheric pressure. See, suppose this is atmospheric pressure, and at this temperature, it will be equal to boiling point. So, dear, this point, this is your boiling point of pure solvent, and this is boiling point of solution. At the same point, you can see that vapor pressure becomes equal to atmospheric pressure. That point is boiling point, and you can see from this graph, this is greater for solution than that for pure solvent. So, this TB minus TB naught, TB is your boiling point of solution and TB naught is boiling point of solvent. So, this elevation, this is known as elevation in boiling point. Okay. Now, the elevation in boiling point, it depends upon the concentration of the solute in a solution. And it is related to delta TB is directly proportional to molality. Okay. Now, for this, we will add Kb into M. This constant is your molar elevation constant, and another name for this constant is ebullioscopic constant. If Kb is the ebullioscopic constant, M is the molality, and delta Tb is the elevation in boiling point. So, dear students, if I will ask, what is the definition of ebullioscopic constant or molar elevation constant? You can say that, suppose I am taking the molarity of the solution is 1. So, you can say that it is the elevation in boiling point when molarity of solution is 1. When molarity of solution is 1, then this molar elevation constant becomes equals to the elevation in boiling point. This is the definition for this ebullioscopic constant. Okay. The units for this case, Kelvin kg per mole. Now, how can you say that this elevation in boiling point is a colligative property? Here, if you remember the definition of colligative properties, what is that? It is a property which depends upon the number of moles of solute and is independent of nature of solute. So how can you say that it is a colligative property? See, if I will open this formula, what is the molality? Molality means number of moles of solute dissolved per kg of solvent. It is number of moles of solute dissolved per kg weight of solvent. Okay. Now, number of moles of solute can be given mass of solute over molar mass And if this if this weight of solvent is in grams, it should be converted into kg. That should be multiplied by, it is divided by 1000. This 1000 goes upward. So you can say that elevation in boiling point depends upon the masses of the solute. So that's why it is one of the colligative properties, because it depends upon the mass of the solute and is independent on the nature of the solute. That's why it is known as colligative property. I hope is it clear to you. If you still feel any doubt, then please let me know. Or if it is clear to you, then give me thumbs up. Fast. Freezing point. So, what is freezing point? Raise your hand, anybody in the class knows what is freezing point? Okay, message me fast. Yes, yes. Freezing point, as the name suggests, freeze. Something is solidifying. It is a temperature at which the solid and liquid form of the substance are in equilibrium, which means the solid and liquid have the same vapor pressure. Okay, that is the freezing point in which solid and liquid state are in equilibrium to each other, or they have equal vapor pressure. This is your freezing point. Now, boiling point of the solution is always greater than that of pure solvent. But in case of freezing point, it is reverse. Freezing point of solvent is greater than that of solution. Remember. Okay. So, we will again explain the freezing point, depression in freezing point with the help of graph. First time drawing, then we'll explain you. Again, I'm going to plot the graph between vapor pressure and temperature. See what will happen. Next one is the solution. Solid solvent. And this is the solution. Now I will explain it. Here, this graph is for pure solvent and for solution. My dear, first on cooling, when we decrease the temperature, the vapor pressure of the solvent decreases along the curve AB. Vapor pressure of the solvent decreases, okay, along this curve. At this point, at point B, the liquid solvent starts solidifying. That's why this temperature corresponds to freezing point of pure solvent, TF. No. Now, the vapor pressure again decreases up to C. At this point, at point B, the liquid solvent and solid solvent are in equilibrium to each other. That's why it is the freezing point of pure solvent. Okay? Now, as at any temperature, the vapor pressure of solution is always less than that of solvent. So that's why the curve ED has lower vapor pressure than that of solvent and lies below the solvent curve. And this point TF represents the vapor pressure of solution. Again, this TF, delta TF in this case will be TF naught minus TF. In elevation in boiling point, it will be solution minus solvent. This is the difference. In this case, this delta TF is also directly proportional to molality. For that, we will put this cryoscopic constant. This KF is your molar depression constant. Or cryoscopic constant. In that case, in case of elevation in boiling point, it was molar elevation constant of ebulioscopic constant. Here it is depression constant or cryoscopic constant. So if I will ask, what is the definition of KF? It is depression in freezing point when molality of the solution is considered to be 1. Its units are also Kelvin by molality or Kelvin kg per mole. Same units. Okay. So, if I will ask, how can you say that it is a colligative property? Now, I am expecting that you should know. Because it is the same concept that we have discussed in elevation and boiling point. Same concept. Kindly open this molality. Molality is number of moles of solute dissolved per kg of solvent. So it will be molar mass of solute, given mass of solute over molar mass of solute into weight of solvent in kg, or if it is in gram, then it should be divided by 1000. As from this equation, you can see it depends upon the amount of the substance. That's why it is a colligative property. I hope is it clear to you. Is there any doubt? Please let me know. Otherwise, raise your hands fast. Fast. Okay. So, what is the importance of this depression and freezing point? It has very important application in melting of ice on the roads. Like in US, there is the temperature is in minus. So, in winter or in hills, where it snows heavily, we use sodium chloride or calcium chloride is scattered on the road. What is the role of sodium chloride? Because there is a heavy amount of ice present on the road, and ice plus NaCl or ice plus calcium chloride, it is very low freezing point. They form the antifreeze mixture. So this mixture has very low freezing point. So they melt the ice and they are not allowing the ice to solidify. So the roads will be clean. Okay. This is the role of melting, role of your depression and freezing point. Okay, dear. That's all about your colligative properties. Next, abnormal molecular masses topic is left, which we will discuss in the next class. If you have any doubt, then please let me know.